Okay, so that was the equation for discharging from that initial value. But if we think about what we've got in our circuit, the initial value of voltage is the EMF of that battery. So the battery is going to give us our maximum value of the voltage on the capacitor. If we need a bigger voltage, we're going to need a bigger voltage on the battery to make it work. Now, sneakily, I've just moved my resistor around here, so slightly different from what we've done so far. If I have the resistor in this section of the loops, then this resistor will always be there for charging up and for discharging. Okay, so the current will always flow through R. If we have that set up, if we're not doing anything complicated, which we won't in any exam questions, if I flick the switch back over to the battery at that moment when we start our stop clock, then what we're going to find is our charge will build up. Our charge will start going onto here as it pads around, it's pumped around, and our charge on the capacitor will build up, as will the voltage on it. So we're going to get a rise in PD. However, it's still controlled by the same factors: how much that can store, how much charge will fit on the capacitor, and how quickly it flows, which will be that. The only difference is you've got your pump in the action. So what we'll find is for the same resistor, you will end up with, a bit far off that, but not too bad, you're going to end up with the same curve heading towards that same maximum value and eventually reaching that same maximum value as which it started at. And hopefully straight away, even with my bad diagram, you can see that those are mirror images of each other. Okay, as we picked up right at the beginning when we were doing the descriptions. Okay, so when we looked at that section, you know, they are that mirror image about that original value. So that makes the mathematics easy, because if we had a value, for example, here on the discharge, or its value is that, the missing extra part is the same as that height there. Okay, so that value of PD there. So if I add that onto that, wherever I am on my curve, you know, that onto that, etc., I will always end up with my total voltage. So charging, although it's a bit more complicated with the battery involved, actually, if we think of it just as pumping the same stuff around at the same rate, then, assuming there's no internal resistance, I should say, then if that's the total resistance, you will get exactly the same mirror image curve. So let's have a look at that idea there. Let's just move that out of the way. Okay, so if we get that, then, as I said, excuse me, we're going to have that maximum value. Maybe draw this a little bit more carefully. So there's my V0, and so I'm going to end up with crossing over at halfway. There we go. My asymptotic curve isn't quite touching, honest. You're going to end up with that lovely little curve there. Okay, so if we were thinking about the Kirchhoff's approach to that, it makes sense, because this, for example, when it's charging, will be my voltage on the capacitor. This will be my voltage on the resistor, going down because the current gets less and less and less. Okay, let's just put that in, equals V discharge. Oh, excuse me, can't spell. But also equals, of course, IR. Okay, and if you want it to be really fancy, dq by dt R. Okay, so it links in with this. The rate of change of that multiplied by R will give you the value of the voltage on the resistor. So even though that's going up, it'll go down, etc. Because that's just a quantity rather than an actual gradient. So these simply add up, which is what we deduced anyway. My two voltages, PDs, will add up to the EMF that we started with. So in terms of the mathematics, we can take the answer from above, and I'm just going to use the most useful one, but you could do it for any of them, but I'm going to use that one. We can simply get the equation that puts them all together. So using that, okay, and we've got the idea that V naught equals V discharge plus V of charge. Okay, what we're going to end up with is, I'm going to put it the other way around because I want the charging now, goes to V charge equals V naught minus V discharge. Yeah, so I'm going to just put that as V. I'll call it C just to kind of signify it. That's going to equal V naught minus the equation that we had before, which was V naught e to the minus t over CR. And just to neaten it up, that's going to equal V naught common denominator 1 minus e to the minus t over CR, which is the equation again that's on the data book, although again they use X because it could be for voltage or charge or current. Okay, but the crucial bit, okay, which we'll link back to in a second, but the crucial bit is what this tells you about this value here. So it's worth noting that the e to the minus t over CR is any value between 0 and 1. Okay, so again, it's a bit like trigonometry, it's a multiplying factor. So values between 0 and 1. Okay, so when it is 1, then 1 minus 1 equals nothing, gives you no value at all. If it's 0, then it's the maximum voltage and so on, so you can figure that out. The reason behind it, again, don't forget, in the end it's all down to Q, so at any point you could do Q naught 1 minus e to the minus t over CR. Okay, so the only difference between two equations is whether it's the value or whether you're subtracting that value from the full value, subtracting it from 1. Okay, so that is kind of the basis for our two equations. Okay, they're both, I should say, you could integrate it through from first principles, so you could do it that way if you want. Challenge for some people to try it out, but it's easier, I think, just using Kirchhoff's, which is more true. But one thing I'll pick up on, and that was, as I said at the beginning, if you can avoid it, you don't really want to start trying to get results off graph. They might ask you to, but it was never going to be dead accurate to get the value or to get the time constant from that. So it's much easier to use the mathematics. Now, of course, if that's your results from an experiment, that's the results from an experiment. Okay, and I'm going to get you to do an experiment and plot the results in two ways. One of them like this, to try and get your values for time constant, and one in a better way. Okay, and that better way links us in with our ideas that we can put this style of equation actually into a more useful format, okay, which is actually one of these. That's quite a nice idea as fractions, but actually this conversion back and forth here is really important, really useful. So do keep practicing this, because a lot of equations will want this, a lot of questions will want this, sorry. And the reason is this, okay? If we can rearrange, hence very important, if we rearrange that, then what we can do is put it into a more convenient form, okay? In other words, if I want to get rid of the exponential, I need to do the second function. So I'm going to logarithmize. I don't know if that's the word. I'm going to put log of v. That's going to equal log of v naught. Okay, and then that gets rid of the log of e, log to the base n multiplied by e, will actually get rid of that completely. So I end up with minus t over, I'm going to put it there, 1 over CR. Okay, just make it nice and neat. Now, if I rearrange that ever so slightly, okay, that, in terms of an experiment, worked really well. That's a variable. My voltage changes. my time obviously changes as well. But if I write this as log v equals, that's a constant because that's a maximum value, so log of a maximum value is still a constant value. Those are constants, so I'm going to write that as minus 1 over CR times by t, okay, plus log of v0. And that, with a variable and a varying quantity, okay, means that if I plot that on the y-axis, because it depends on time on the x-axis, I'm going to end up with a gradient of that and, excuse me, terrible x, plus a constant, an intercept constant of that. Okay, so if I do that with data, I should end up with a perfectly straight line, and if it's slightly wobbly, then you can do a line of best fit, which will get rid of any uncertainties created by random errors, because you're always going to get a little bit of random errors, although to be fair, capacitors are pretty spot on. But if you did this with radioactivity, you'd still get a straight line, and radioactivity isn't spot on. Okay, so we'll come back to that at the time. But yeah, so that means that I've got here log of v0, so I can find the original value, okay, without knowing it, I can still find what the maximum value was. And I can get from this that my gradient, which I will not draw full size, but I'll do it for illustrative purposes, that is going to be equal to 1 over CR. Okay, don't forget it is a minus gradient, so don't forget the minus in there. But yeah, so this actual value itself, modulus of it, i.e. not worrying about the sign, will equals 1 over CR. Okay, now that does mean it's a really, really good way of finding your way around everything. Okay, it's a really good way of finding simple answers to it. Okay, but this idea is really good. However, there is one thing, and this is one thing to bring in about practical technique. If you are trying to do this, write this down, put a table header on what it's written as, I'll say e.g. table header, because that's probably where you're most likely to see it. Okay, then what you get is you'll see this written as log of v, for example, over v. When you see that, don't think it's v divided by v and then logged. This is why we don't use brackets around units. This means, okay, so means log of v, where v measured in volts. Okay, you could have, e.g., log of v, but in millivolts. Okay, and if you converted that into volts instead and found the log of it, the log would be a completely different number. Okay, so that's why this is important, and this is why we don't tend to have brackets around the original variables. Let's just think, if you were to have, for example, log of v in v, that looks even worse. Okay, I should point out that the log itself is just a number, so logs don't have units. Okay, it's just a mathematical function. So just be really wary of that. That's why you tend to see this. So you do need to make sure your units are in if you're doing this, but it's more like you'll see that in an exam. Okay, if I was to give you a value, let's say 0.21 volts, I'll put a little just v in there, okay, 0.21, excuse me. What you find is, and you can double check this, I did a quick calculation before, but that'll be minus 1.56. Okay, whereas log of, let's put it another way, that's 210 millivolts, 210 millivolts. Okay, so in millivolts, what you'll find there is you end up with 5.35 plus minus. They're completely different numbers. Okay, so be wary of that. It just means you'd still end up with the whole working, but you just need to make sure that everything's in the same units. Okay, it just means it give you a higher value or a smaller value. So to round off, let's bring it together. Sometimes we might need to find things, for example, the time constant, or a capacitance, or a resistance, etc., etc. So the other reason for knowing this conversion, okay, really important conversion, is that without a graph, they might ask you to find out the value of t, or say, or anything, any in this constant. Okay, and if they want you, if they want you to find any of those constants, then you need to get logarithms to get rid of all the patterns down here to make that nice and clear and straightforward. In other words, to give you this, because once you've done that, clean that up out of the way, then it's just constant divided by constant equals, and it's just rearranging. So again, for an example, a little walkthrough, if I wanted to find the value of time constant, okay, so let's just go with that, in other words, tau. Okay, if you want to do that, then that happens to equal RC, so I've got T over tau, okay, but I'll make it more obvious when we do it. So let's just rearrange. So either subtract, or probably easier to just do it as a fraction. They might say, how long has it taken to reach, or what's the time constant if it takes 3 seconds to get to a value of a third? 1/3, log of 1/3. So that's more convenient way of doing it. So if we get rid of logs, then we've got rid of, that exponential straight away. Okay, and then if we want our CR part, then all we need to do is rearrange. So CR, or I'll put in a tau just to over there, but is equal to CR equals, and you just rearrange it, again, minus T over log of V over V naught. Okay, so maybe that's helpful, maybe it's not. One thing I should point out, okay, and it doesn't matter if this is on the top or the bottom, so I'll put this in brackets. If you do this, I'm going to make it very obvious. If I want to make that plus, then what I do is simply turn the fraction upside down. Okay, so a little trick there, just note that. So swapping the fraction over before you log it makes it from a minus number into a positive number, negative to a positive number, or vice versa. So again, notice here, that's a fraction, so it gave us a minus value. If it's not a fraction, i.e. 210, then you get a positive value, and that's what's going on with that, and that's why you get different values completely. Okay, so just be aware of that. I'm sure you've done it in maths, or you will do it in maths. Okay, but it is important. This technique, swapping back and forth, is really important. So again, practice. Okay, slightly different from that one. As I say, subtracting them is sometimes useful. Doing a fraction is sometimes useful. But don't forget, the opposite function of your E is the second function of the same button on your calculator. So it's the same button, just second function before you push it. So always really useful. Okay, so guys, a little bit of notes at the bottom for you to read. Okay, and this is where the bits about Kepler's third law and things come in. So you can use logarithms there, because it's all a way of getting rid of powers. Okay, so what we can do is actually do a log of time, for example in Kepler's third law, rather than time cubed. Time squared is proportional to r cubed. Okay, so we can get around that. So I'll share some questions with you on that as well. Okay, thanks very much. Part B. It's a long idea, that.